Okay, last class we explained the design criteria and how to design both the vertical curve, the crest, and the sag curves. And we had an example for this. Then we solved. Okay, the last thing we want to design here, or the case. Oh, we didn't explain this case, which is basically the undercrossing clearance. Okay, so that's the case where we have a bridge, okay, going over a vertical curve, or a vertical curve going underneath a bridge, and that's the clearance. So this basically what we want to check here, if a driver trying to go under that curve, under in this underpass, that he can see sufficient distance in case if there's an obstacle here at height h2, okay, then he can see it at the stopping, if that's the stopping distance. Okay, so basically the equation for that is L, that's the first case, that the side distance is greater than the length of the vertical curve. So this is the case 2s minus 800 c. C, that's the vertical clearance in meters. H1 plus H2 over 2 divided by A. A is basically the algebraic difference in grades percent. H1 and H2. H1 in this case would be the height of the eye of the driver, and H2 is the height of the obstacle. In this case specifically, what we are concerned about are truck drivers, because they are sitting at a high, higher than regular cars, so they are sitting usually at 2.4 meters, and the obstacle is 0.6. Here we have, if the side distance is less than the length of a vertical curve, then we have this equation, as squared divided by 800 c minus h1 plus h2 over 2, the average height. So let's solve this example. So what we have here, we have given that the design speed is 90 kilometers per hour, and the minimum clearing height is equal to 4.5 meters. Answer the following. Design the vertical curve connecting between the two grades, assuming no bridge. Then determine the maximum allowable depth for the girder of the bridge here. So that's the pavement surface. Here, that's the information. For the determined girder depth, check side distance clearance under the bridge. So first of all, we start here and design our vertical curve. First, we start with calculating S, stopping side distance. So here it's 90, we have 90 kilometers per hour, so it's 90 over 3.6 multiply 2.5 plus, this would be 25, by the way. So 25 squared divided by 2 multiply 9.81 multiply F plus or minus, okay, F plus or minus 0.01 g%. In this case, what is the value of G? We're going to take the worst case condition. Can someone tell me? we're going to, excuse me,
J2.
G2 minus 4%. Okay, this is what you want to say.
Yes.
Remember, this is minus if you are coming from this way. But if there is a vehicle coming from this way, then this becomes minus and this becomes plus. Okay? So we are going to take the worst case condition, which is if a vehicle is driving from this side. So this. Okay? So this is basically equal to 62.5 plus 25 squared divided by 2 divided by 9.81 divided by 0.345 minus 0.08 plus 62.5. So this would be 120.2. So the total will be 182.7 meters. Now we want to determine the length of the curve. So let S less than L. In this case, the design equation in the situation will be the design equation for that case will be what? Okay, could you hold for a second, please? So in this case, L equal A S squared divided by 200 multiply 0.6 plus S tan 1 degree, which is basically A S squared divided by 120 plus 3.5 S. So A in this case would be the absolute difference between G2 and G1. So here we're going to take the positive and the negative. So it's plus 8 minus 4. So it's 12. So A is 12. So we have here 12 multiply 182.7 square divided by 120 plus 3.5 multiply 182.7 square. Not square, no, without the square. So this would add up to 12 multiply 182.7 square divided by 120 plus 3.5 multiply 182.7. So this will be 527.4 meters. Then take L equal 540. So this is the design length. Now we want to calculate the Bvc and Bvt, but before doing this we need to make the checks for the safety of this design, because it's a sag curve. Then here check for here the sag curve. Checks. We have the appearance, L minimum should be 30A. That means it's 30 multiply 15. So this would be 30 multiply 12, sorry. It's 30, I'm sorry. It's 30A, that means 30 multiply 12. So this will be basically 360 meters. That's the minimum for this difference in grade. So 360 meters. So we are done with this because we have 540. So that's the first check. The second check is for drainage. So L over A should be at less than 51. So in this case we have 540 divided by 12. This is equal to 540 divided by 12. That would be 45, which is less than 51. Okay. The last check is basically for comfort. For comfort, we have L minimum would be A V square divided by 395. So we have 12 multiply 90 square divided by 395. So this will be 12 multiply 90 square divided by 395. So this is 246 meters. Okay, and we are greater than this, so this is okay. So our design value here is acceptable and meets the requirements for a sag curve. Then we move and check now for the clearance. For the clearance here to see okay. So basically, okay, what he is asking for here is determine the maximum allowable depth for the girder of the bridge. So in order to do that, we need to find the elevation of this point. So let's calculate first the Bvc and Bvt. So here for the Bvc and for the Bvt. The station for Bvc equal the station for the BVI minus L over 2. So here we have this station would be, that's the station of the BVI. So we have 2 plus 358.5 minus L over 2, which is 540 divided by 2. So this is 270 minus 270.0. This will be 0.5, and here is 8, and here will be 3, 0, not 3, I'm sorry, 8, 0 plus 2. So that's the station of the PVC. For the BVT, the station for BVT equal the station for the PVC plus L. So basically it's 2 plus 088.5 plus 540. So this would be 0.5, and here 8, and here we have 12, 6 plus 2. So this is the station for the PVT. For the elevations, let me just erase this. For the elevation of PVC, it's equal to elevation of BVI plus L over 2 multiply G1. And G1 here we take it as an absolute value. So this will be plus 260.25 plus 270 multiply 0.04. So this elevation would be 260.25 plus 270 multiply 0.04. So this is plus 271.05 meters above mean sea level. And we'll do the same here for the BVT. The elevation for BVT equals elevation of PVC plus L over 2 multiply G2. So here we'll have plus 260.25 plus 270, that's L over 2 multiply 0.08. So the elevation for the BVT equals 280 plus 281.85 meters above mean sea level. Now we need to check if what we are doing is correct. How can we do that? I will show you now. First, let's define the equation for this vertical curve. The equation for this vertical curve will be y of x equal a x squared plus bx plus y naught. So y node, as we mentioned, is basically elevation of the BVC. B, that's G1. A, that's G2 minus G1 over 2L. Clear? X is basically the distance from the BVC. So let's calculate A equals G2, which is plus 0.08 minus 0.04 divided by 2 multiply 540. So this would be 0.08 minus 0.04 divided by 2 divided by 540. So we have here 1.11 multiply 10 to the power minus 4. So basically y of x equal 1.11 multiply 10 to the power minus 4 minus 0.04 I'm sorry, this is multiply x square. Here multiply x plus the elevation of that of the BVC. So the elevation of the BVC is here. So this is plus 271.05. Now we want to check if our calculations here was correct. So we will try to substitute in this formula and find the elevation of the BVT. So in this case, the BVT, if that's BVC, and here is the BVT, x will be the length of the curve. So let's calculate y at 540. That's at the end of the curve. So we have 1.11 multiply 10 to the power minus 4 multiply 540 square minus 0.04 multiply 540 plus 271.05 equals times 540 square minus 0.04 multiply 540 plus 271.05. It's 281.85 meters above mean sea level. Let's see what was the value here. The same, exact. So we are doing fine. So this equation is correct. This formula for the curve, okay? And so now we move on to determine the allowable depth of the girder. So we want to, let me just zoom in. Guys, what we need to do is basically to find the elevation of this point right underneath the bridge, okay? And we are going to take this point at it's at station, at this station 2000 plus 325. So we're going to subtract it from here and get this x bridge. And let's we are going to substitute to get the elevation here. So x bridge equal the station of the bridge of station for the bridge minus the station for the BVC. So it's the station of the bridge, which is 2 plus 325.5 minus that's the station of the BVC. So here 2 plus 0.88.5. So here we have 0, we have 7, we have 3, we have 2. So we have 237. So XP equal 237. So let's find the elevation of the pavement surface at this point. So Y at Y bridge, it will be at 237 equal 1.11 multiply 10 to the power minus 4 multiply 237 square minus 0.04 multiply 237 plus 271.05. So this elevation would be 1.11 to the power minus 4 multiply 237 square minus 0.04 multiply 237 plus 271.05. So here it's 267.8 plus meter above mean sea level. So that's the elevation of that critical point, which is right underneath the bridge. Now the clearance required okay, so that's the elevation of the bridge. So that means based on this condition that that's the elevation of the bridge. So basically there is no room to do anything. Actually the girder depth I think this was not this there was a mistake here, and I think this was supposed to be plus 2 6 I think it was 3 meters 3.5. So the girder depth here we have a bridge and the allowable distance for a girder is here. We have the elevation here, it's 263.5 meters, and the pavement surface is here, it's I'm sorry, it's the other way around, 267.8, and this should not be this way. Okay, I think this is supposed to be 271 meters. So in this case, what we have 4.5 clearance height. So we want to find D. As we can see, the girder depth will be GD equals the elevation of the bridge deck, which 271 minus 4.5 minus 267.8. So if we do this, we will end up with 271 minus 4.5 minus 267.8. Oops, so now it's minus 1.3 meters. So what does this mean? This means that we cannot build the bridge this way, because basically, you know, the clearance to begin with between the bridge and between this elevation and this elevation of the pavement is basically less than 4.5 meters. So let's try this. We want to get this elevation down by a distance. How much is this distance? 1.3. That's to meet this criteria. Then we are going to assume that we need a girder to be at 1.2 meters depth. So basically the target pavement elevation is 267.8. ده اللي هو كان منسوب الطريق هنا يا شباب. اوكي، minus 1.3 minus الدبث اللي احنا هنحطه اللي هو 1.2 مثلا. For example, it's 1.2 meter for. So what we need this to be is basically 267.8 minus 1.3 minus 1.2. So we want this to be 265.3 meters above mean sea level. How can we do that? I will show you now how we can do that. We can go back to our design and change the length of the curve and try to, of course, if we need to change the length of the curve, then we are gonna change the stopping side distance. How we can reduce the stopping side distance? By reducing the design speed. Instead of having 90 kilometers per hour, we can go and reduce this to be maybe 80 kilometers per hour to match the new length that we are gonna select. Clear يا شباب؟ Okay, we're gonna take a break and we'll be back after 10 minutes. Okay, now what we want to achieve, we want to increase the clearance between the pavement and the curve and the bridge. Let's just take a side note here. If we have a sag curve like this condition, and here's this Bvc, and we are going this way, that's our vertical curve. If we want to bring this down, what we need to do is basically using a shorter length. If we use a shorter length, so that was the beginning or the initial length, L1. If we reduce the length, we bring it down. In case of, this is for sag curves. In case of a crest curve, okay, if we have a curve like this, and that's Bvc, and we want to increase the clearance here. If we want to increase the clearance, we increase the length. and this way we bring this down, so this way we are increasing the clearance. Clear? So in our case, what we are aiming for is basically reducing the length of the curve. So here the initial length we had 540, and our target is basically reducing the elevation of the pavement at underneath the bridge by how much? By so basically the target elevation is 265.8. So we want to reduce the elevation of the pavement by 2.5 meters. How can we achieve that? We will try to achieve that by solving this issue here. We want to reduce this elevation to be 265 I'm sorry, reducing this by 2.5. How can we do that? Let's see. This is the one that we can change here. So we want to achieve, we want to have the Bvc equal the elevation of Bvc. The new elevation should be 5.762. Should be like this. So that means if we subtract the BVI from it, 260.25, so we have here 3.7. So that should be equivalent to the new L over 2 multiply 0.04. So the new L should be at least here it's gonna be 7.35 multiply 2 divided by 0.04. 7.35 multiply 2 divided by 0.04. So the new length needs to be 367. So let's have L dash equal 360. Okay? And let's see if with that length we will have the clearance that we needed. So let's check on that. Of course, we need to reformulate the equation or the formula, the formula for the curve. So we have here y b dash. We need to calculate the station, the new station for the Bvc. So the Bvc station dash for the Bvc would be 2 plus 358.5 minus L dash over 2, which is basically 360 over 2, which is 180. 2 plus here 5.871. So this is going to be the station of the Bvc, and the elevation of the Bvc, that's the new elevation, is going to be this value plus 267.55. No, actually it's going to be less than that. It's going to be 260.25 plus 360 divided by 2 multiply 0.04. So this would be 260.25 plus 360 divided by 2 multiply 0.04. So this would be 267.45 meters above mean sea level. So let's now check or reformulate the equation for the bridge. So we have y dash of x equal a dash x square plus bx plus y node dash. So the new a dash, so a dash equal g2 minus g1 over 2l dash. So it equal to 0.08 minus 0.04 divided by 2 multiply 360. So this will add up to 0.12 divided by 2 divided by 360. 1.67 multiply 10 to the power minus 4. So this would be 1.67 multiply x square minus 0.04 x plus the new elevation for the BVC, which is basically this value, plus 267.45. So we need now to calculate the new elevation underneath the bridge. So y dash for B, we need to calculate the x, the new x for the bridge, because now we have the new station for, or the beginning of the bridge changed, as you can see here. So the x of the bridge, x dash of the bridge equal okay, let's calculate it from here. That's the x of the station of the bridge, 2 plus 3 to 5.5 minus the new station for the BVC. The new station for the BVC it's over here. So this is 2 plus 178.5. So here we have 0.741. So that's the new, the x dash, 147. So let's substitute and see if we will be able to achieve safe elevation at this point. So here we have 1.67 multiply 10 to the power minus 4 multiply, what was that again? 147 square minus 0.04 multiply 147 plus 267.45. So the new elevation in the new bridge will be, in the new curve, sorry, minus 0.04 multiply 147 plus 267.45. So here is going to be the new elevation is going to be 265.17 meters above mean sea level. So basically now we are below this value. So the girder depth equal 271 minus 4.5 minus the pavement elevation underneath the bridge. So the maximum girder depth you can have is going to be 1.33 meters. in order to maintain a clearance of 4.5. Now, we want to check to make sure that the new changes that we made is going to be safe and so going to be acceptable. So first of all, we want to calculate the stopping side distance, and based on that we determine the speed, and we want to check if this is going to be acceptable in terms of the drainage and the appearance and the comfort. So now we have achieved this this constraint. Now we want to go back and check on our new curve, this value. We want to check on that to make that it is meeting the appearance requirement, the drainage and comfort also, and we need to determine the speed, the safe speed for this curve. So here we need to check for the appearance. Okay, we have L minimum equal 30A, which is basically 360. That's equal to this. So this meets the minimum requirement for appearance. So this is acceptable. L for the drainage, L over A. So that's 360, okay, divided by A, which is 12. So this would be 540 divided by 12. This is going to be 45. It's less than, 360. This is going to be 30. This is less than 51. So for the drainage, it's acceptable. For the comfort, let's assume that V dash equal 80 kilometers per hour, and let's see. So L equal AV squared divided by 395. So we have 12 multiply 80 squared divided by 395. So this would be 12 multiply 80 squared divided by 395. This is going to be minimum 194 meters, and we are meeting this condition also. So with this length, we have all the other parameters are acceptable. We need to check now on the speed and check whether this speed is going to be acceptable, or safe for this vertical curve. So let's now calculate the stopping side distance for the new speed. So we have 80 divided by 3.6 multiply 2.5 plus 80 divided by 3.6 squared divided by 2 multiply 9.81 multiply 0.345 minus 0.08. So the stopping side distance in this case would be 80 divided by 3.6 multiplied 2.5 plus 80 divided by 3.6 squared divided by 2 multiplied by 9.81 multiply 0.345 minus 0.08. So this is going to be 150.53 meters. So let's check, on the design formula that we have before, that L equal the length of the curve equals A S square divided by 120 plus 3.6 S. So we have 12 multiply 150 square divided by 120 plus 3.6 multiply 150. So 12 multiply 150 square divided by 120 plus 3.6 multiply 150. So this will give us 409.1 meters, which is slightly greater than 360. So we need to reduce the speed even more in order for this vertical curve to be safe. So we need to reduce the speed, okay? So actually we need to reduce the speed to be maybe 70. Stopping side distance equal 70 divided by 3.6, and we try this way until we reach the acceptable, that the length, the design length will be within the acceptable limit. Any questions so far? The last point here was basically to check on this clearance, whether it's going to be safe for trucks to drive underneath, and there's sufficient side distance to check for that. So here we need to make that final check, which we were explaining today. We need to make that check, okay? That's the line of sight with the giving length and everything, okay? That this is, acceptable. So we're going to take this equation with us, and we're going to go here. That equation for the case 2 side distance less than the length of the vertical curve. And basically, this is what we have here. So let's check L. In this case will be AS square. A in this case is 12 multiplied by 360 square. No, not 360, I'm sorry. We're going to take this stopping side distance as it is, divided by 800 times C. C, that's the clearance, which is 4.5 minus H1 plus H2 divided by 2. H1, that's the height of the eye of the driver. In this case, we are taking the height of the eye for a truck driver, so it's 2.4. Plus H2, that's an obstacle, which is 0.6 divided by 2. And let's see. So we have 12 multiply 150 square divided by 800 divided by was 4.5 minus 2.4 plus 0.6 divided. Okay. Uh, 2.4 plus 0.6 divided by 2. So L is, the minimum L is 112.5 meters. So we have L greater than this. Okay, this is, I'm sorry, this is L is less than the one that we have, which is 360 meters. So we are on the safe target. Any questions so far? Okay, that will conclude our lecture today, and hoping to see you next week, inshallah.